Well, a very happy Tuesday evening to you all. Thanks for joining us. If you're watching on YouTube, we have a YouTube live stream and also then a recording that's going to be available subsequently. And we also have a live Zoom classroom with 14 students in the classroom at the moment. That number may change. I'm the instructor for this evening, ham radio call Whiskey 4 Echo Echo Yankee. My name's Gary. And we're going to be in Chapter 5 tonight. And when I talk about the chapters, I always like to show you the book. This is the American Radio Relay League License Manual for the General Class, the 10th edition. This is the book we use, and we'll be going chapter by chapter for the rest of the class. As I mentioned, tonight is Chapter 5, Radio Signals and Equipment. And to get us started off, some of this may be review to you, especially if you took my technician class to get your technician license. But we'll get into some new stuff here in just a bit. But to start us off, I just want to remind you that, there we go. Modulation, the topic of modulation. When we turn a transmitter on and just send a radio carrier out on the air, it doesn't really mean anything. There's no information being conveyed, but by some means we impose information on that radio carrier, and it's carried to a far distance. It might be our voice. It might be turning it on and off in a Morse code pattern so that somebody at the opposite end can decipher the message that you're trying to transmit. So modulation is adding information to be carried by a radio frequency carrier. What we're looking at here is amplitude modulation. This was the first voice mode. So that the top indicates an audio frequency of some type. This is a sine wave, of course. And a radio frequency carrier much, much higher. This is, 1,000 hertz. This is in the megahertz, And when we impose amplitude modulation, if we were looking in the time domain, where the vertical axis is amplitude and the horizontal axis is time, this is the combination of those two. This is the modulated envelope. So amplitude modulation changes the instantaneous power level of an RF carrier to contain information. And here again, we're looking in the time domain, amplitude on the vertical scale and over time. So this is what an oscilloscope, for example, would show you if you had it at the output of the radio frequency transmitter. Now, we also like to look at signals in the frequency domain. And when we do that, this is what it looks like. Signal amplitude, again, still on the vertical scale. But instead of time on the horizontal, we actually are looking at frequencies, lower frequencies, higher frequencies, and then even higher frequencies still. And so for an AM signal consists of 3 components: a carrier, that's this right here in the middle, and if there was no modulation, you'd still have the carrier at full power. But when we add modulation, we add information that is both below the radio frequency carrier and above the radio frequency carrier. Above, it's known as the upper sideband. Below, it's known as the lower sideband. So AM consists of lower sideband, carrier, and upper sideband. That's amplitude modulation. We'll take a look at an actual signal here in just a sec. Frequency modulation, if you've got one of the little HTs, those are FM radios. And instead of changing the amplitude of the radio frequency carrier, what we do is we keep the radio frequency carrier at full power all the time, but you change the frequency. So here it's higher in frequency, here it's lower in frequency. This is kind of exaggerated, but higher in frequency. So you get the idea. It's in step with the audio modulation that we're showing up on top. So for an FM, it changes the instantaneous frequency of an RF carrier in order to convey information, because that's what modulation is all about. Another type of modulation that is a cousin of FM is known as phase modulation. And phase modulation changes the instantaneous phase angle of an RF carrier in order to convey information. Here's the RF carrier up on top. Here's the modulating signal. And this is what the modulated signal might look like, in this case with a sine wave modulation. Here's an animation which shows now the modulating signal in this case is a ramp voltage. And you can see that it's kind of changing in frequency. You can see it wider and then narrower. There are some glitches and whatnot, but the modulation with phase modulation changes with both the amplitude of the audio signal and the frequency of the audio signal. The higher the frequency, the more phase modulation, the more deviation will occur. So just keep those facts in mind. All right. Come back to me just for a second. I'm so excited about ham radio. I love ham radio, but I'm going to say something derogatory, well, maybe not, but about hams. So I say that ham radio operators, well, come back to the laptop, hams are opportunistic. What do I mean by that? Well, we try to take advantage of situations that are going on. Here I'm talking about propagation. We're strategic, we're shrewd, we're astute. Oh yeah, pat myself on the back. So anyway, we take advantage of existing conditions. Are there sunspots going on? Is the band open to the region that I want to communicate with? Is there a DX contest running this weekend that I can make contacts in? There's a really big DX contest coming up this weekend, by the way, the ARRL single sideband contest. So you'll see lots of stations on the air. So hams are opportunistic. In contrast, the telecommunications industry is always seeking reliable communications. They don't want communications to be hit or miss. If they're putting up a system, they want it to work, and they want it to work at all time, especially if they're putting up something called a radio link, which is a circuit between 2 points. And in amateur radio, one of the shared bands that we have shared with Wi-Fi, 2.4 gigahertz, or the 13 centimeter band, amateur radio operators are putting up what we call mesh networks, or it's kind of an independent linking of modified routers using amateur radio call signs and amateur radio software. And so ham radio mesh networks are point to point. And so we need to actually start thinking like telecommunications companies when we're putting these things together. And so what we consider are radio path losses. If we're going from point A to point B, what is intervening? What is the atmosphere going to be like? There's free space loss. Are there obstructions? Is there going to be diffraction? Are there going to be reflections from other areas that might cause multipath? Absorption of signals by foliage or trees, terrain issues, pollution. Can sometimes cut down, especially at UHF and above, radio frequency energy. So one way you can use free space loss calculators. They're available online. And so for our example here, we're going to look at a 2.4 gigahertz 10 watt transmitter with a path loss between points A and point B of 124.2 dB. And we know that to receive a minimum acceptable signal, we need to be receiving at least minus 80 dBm. So this is why engineers on these kind of systems really like the decibel, because it helps in calculations. A little confusing at first, but I think you can get it. So again, we're looking at here, we need to have we have the path loss of 124.2 dB, and we need to have at least 80 dBm, which means that we have to have a system gain of at least 44.2 dB. And then for fade margin, to make sure that we still have a signal, we're adding 10 dB. So we're saying now that the system gain, whatever system we design, has to have a gain of 54.2 dB. And gain can be any of these things: transmitter power, transmitter antenna gain, receive antenna gain, but then we also have to take away any transmission line losses. All right, so we've talked about output power, but how does that correlate with what we're talking about now? Well, so transmitter output power, 0 dBm is the same as 1 milliwatt from a 50 ohm transmitter. 1 watt is 30 dBm, and 10 watts, that's the system we have, has an output power of 40 dBm. This is the ratio. And so remember we said we wanted a desired system gain of 54.2. So we've got to come up with an additional 14.2 dB somewhere along the line in antenna gains. And so this link budget, this is what we're developing of system gains, output power, losses, and antenna gains, maybe at the receive end. All of these things account for all of the power gains and losses in a system. That's called the link budget. So if you're putting together a mesh network or even a remote receiver for a repeater, this is the kind of thing you want to take into account. And link margin is the headroom in a system's design. It's the difference between the system's design level and the minimum power needed to receive a signal. Remember, we added in 10 dB in our example. It's especially important with digital signals. So I'm just introducing this topic to you now. We actually go more in depth with this in the extra class. We'll actually work with some numbers, but I just want you to know about this now. And that takes us to questions. So let's see if we can answer some questions from section 5.1. So what is the name of the process that changes the phase angle of an RF signal to convey information? What do you think?
Bravo. Alpha.
Not alpha.
Bravo.
It is Bravo. Phase modulation. Modulation is adding information to a radio frequency carrier. And what is the name of the process that changes the instantaneous frequency of an RF wave to convey information?
Delta.
Yeah, I think, yeah, good. Delta frequency modulation. And what type of modulation varies the instantaneous power level of the RF signal?
Delta.
That's amplitude modulation. You're changing the amplitude, indeed. And which of the following phone emissions uses the narrowest bandwidth? We'll show you this in a second. What do you think?
Alpha.
Yes, single sideband. Of the choices we have here, yes, single sideband. And what is a link budget?
Charlie.
It is.
Yeah,
No, it's Charlie. The link budget is the sum of transmitter power and antenna gains minus system losses as seen at the receiver. When in doubt, sometimes the longest answer is the right one. Students have told us that. All right. And what is link margin?
Bravo.
It is. It's the difference between received power level and the minimum required signal level at the input to the receiver. So if you get a stronger signal than you need, you've got a margin of error. All right.
What was the answer?
Yeah, section 5.2 it is. Yeah. So radio's building blocks. And one thing that we'd like you to continue on your amateur radio learning after you leave the class here, because we want you to know your radio and to know the signal that you're going to be transmitting. Knowing those characteristics are important. So no matter what radio you have. So here's a question. When you tune your radio to a particular frequency, the frequency display indicates something. What does that mean? Read down at the bottom. And unless your manual states otherwise, it indicates where a carrier frequency would be if the modulation were to have a carrier. Oh, what are you talking about, Gary? So let's go back to our AM signal, for example. The radio frequency that's going to be indicated on the dial of the radio is going to be this frequency right here. And if we were transmitting an AM signal, it would have a lower sideband and it would have an upper sideband. But this is what the dial or the digital readout is going to be indicating. And with that, I'd like to go ahead and move over to our display area where I have the Flex Radio Maestro. This is a little Maestro here on our animation. So come on with me. And so you can't see it very well, but over here in the corner, this is a Maestro C from a Flex Radio. It is connected to my software-defined radio, which is down in my workshop, just one floor below us here. And we have it now tuned to the 40-meter amateur radio band. And what I want to show you, and it has the display here, but we've enlarged it back here to make it a little easier to see. So. Note here that the radio is tuned to 7.250 megahertz. This corresponds to the yellow line you see here. It says A because this is our VFOA, or they call them slices in Flex Radio. And I'm gonna mistune the radio here just slightly. See that spike right there? This is an AM signal. In fact, this is an international shortwave broadcaster. I don't know who. But the 40-meter band is a shared band between amateur radio operators and international broadcasters. So this is perfectly normal. And hams at night on the 40-meter band have to take this into account. There are some frequencies that they may not be able to use. But if I go back and retune the radio back to 7250, so that's the radio frequency carrier. That corresponds to the radio tuning. And then international broadcasting, the bandwidth is -5 kilohertz, +5 kilohertz. So I've actually widened out, if we go over here, to be able to receive AM 10 kilohertz total bandwidth. Now, in amateur radio, we don't go that wide, generally. Normally, we go -3 kilohertz, +3 kilohertz, so we can go to the Maestro, to the menu, and I'm just going to reduce the bandwidth down to our normal communications bandwidth for an AM signal. So you can see it's still tuned at that frequency, but it's only going now 3 kilohertz down, 3 kilohertz up. We'll turn the audio up. I don't know what's going to be here and what language. Okay, well, whatever it is, we're connected up to my DX Commander vertical antenna. That's what we're using here for the radio. So here's an international broadcaster broadcasting AM with a lower sideband and an upper sideband. Here's another over here with the carrier coming up with lower sideband and upper sideband. That's an amplitude modulated signal. All right, let's go on back over. So in the single sideband mode, remember single sideband, we are going to eliminate one of the sidebands and we're going to eliminate that radio frequency carrier. But your radio is going to indicate on the readout where the carrier would be. And in this case, since we're on the 20-meter band, or 14 megahertz, by convention, we're above 9 megahertz, so we're typically going to use upper sideband. So that's indicated here. And so what it is our signal, when we transmit with a 3 kilohertz bandwidth, is going to start at 14.235 and go up to 14.238. 3 kilohertz above that. That's what we want you to keep in mind is, where, when I'm transmitting, where is my bandwidth? What am I going to be occupying? Going back to the 40-meter band with an occupied bandwidth of 3 kilohertz again, if we're here on a 7150, lower sideband, the signal is going to go down to 7147. I ask, what class of license does this ham have? Well, we hope they have an advanced class or an extra class, because if you look at your color chart, this is a part of the 40-meter spectrum that is reserved for advanced and extra class operators, which is why we want you to ultimately get your extra class so that you can occupy these frequencies as well. Here back on 20 meters, it's above 9 megahertz, so it's upper sideband. Below 9 megahertz is lower sideband. Again, the occupied bandwidth is 3 kilohertz. Well, our radio is indicating 14,350, but we have 3 kilohertz, so our signal is up 14,353. What's wrong with that? Well, if we look in our color chart, we're going to see that the top end of the 20-meter band is 14,350. If we're transmitting now on these, we're out of band. We are not authorized to transmit on those frequencies. So we always want you to keep in mind, how close to the edge are you? Whether it's the upper limit of the band, or it's that area where you are authorized as a general class operator to operate, but you don't want to get into the advanced and extra class portions as well. So let's have another Maestro moment. Let's go back over and let's find some single sideband signals as well. We won't dwell on this a lot, but I want you to be able to see the actual signals. So I'm going to change here to lower sideband in the radio. So now you see that we're only receiving the lower sideband, and if I tune down in the band, I want to get a nice clean signal if I can. There's okay. Oh, I like him better. No, that might be an AM signal actually. That's a sideband signal there. I'll turn the volume up here a little bit. So this is an amateur radio signal, a lower sideband signal on 40 meters, occupying no more than 3 kilohertz bandwidth. Actually, the bandwidth I have selected is 2.5 kilohertz, so that's even the narrower than you might think. But that's an actual live signal on 40 meters right now.
Where does the carrier live then? If the sideband is between like 350 and 353 on the upper side, and it's on the lower side is between 47 and 50, then where's the carrier?
This is the magic of the receiver. So for single sideband, remember, we're only transmitting the sideband. We're not transmitting the carrier. And what the radio does is on the receive end, it injects a false carrier from a device we're going to look at it a little later called a beat frequency oscillator. And that false carrier substitutes for the original carrier and then allows you to demodulate the single sideband signal. If you try to tune in a single sideband signal with a conventional receiver without a BFO, without being designed for single sideband, you won't be able to demodulate it, because it doesn't have a reference. You have to put that reference back in.
Got it.
So here we have, again, we're looking at our IEM signal, and we want to compare that we're transmitting either the lower sideband like we saw there on 40 meters, or upper sideband like we might see on 20 meters. You may hear that single sideband has more talk power. I don't know if you've heard that, but for CB, for example, when they introduced single sideband for Citizens Band, they said, well, it has more talk power. Why is that? They're both amplitude modulated signals. Well, it has to do with your radio and your output power amplifier in the radio. Let's say it's a 100-watt power amplifier. Well, with an AM signal, which the early CB was all AM, you had to transmit lower sideband, you had to transmit upper sideband, and you had to transmit that carrier signal. So you had to divide that 100 watts among those signals. So okay, you'd get an amplified output, and you'd make contacts, and that would be fine. With single sideband, you eliminate 2 of the 3, so let's say upper sideband only now. The RF amplifier, the 100 watts, can work just with that and amplify that stronger. So that's why single sideband goes farther than comparable AEM, because you're not having to transmit redundant information. All right, to complete our tour here, let's talk about Morse code, or CW, continuous wave. I don't know if you have any plans to learn Morse code or to operate in Morse code, but again, the indicated frequency here on your radio is the frequency at which you will transmit. We're not going to get into side tone, there's an audio offset, but that's the frequency that you'll transmit. And you'll say, well, I'm just going to transmit on just that one frequency, right? No. When you modulate a transmitter with Morse code, you actually widen the signal out from being just that single frequency to actually having a small lower sideband and a small upper sideband. And so bandwidth of a Morse code transmitter depends on the transmitter's keying rise and fall times and some other characteristics, the speed of transmission, etc. Typically, 150 hertz is the bandwidth for CW signals. So let's finish up here. Let's go over to the Maestro again and take a look for some CW signals. So if you look at the color chart, you'll see that CW signals live in the lower part of the band. So I'm going to dial way down here. Digital.
728 to 750 is the.
Yeah. I don't operate CW, so I'm out of my element here.
Anything in there should be.
There we go.
Yep.
There, right there. You can almost, if you look at the screen, you can almost see the dots and dashes. In fact, I'll expand that out. Oh, and if you don't know, the top half is a spectrum display like we would see with a spectrum analyzer with amplitude and frequency. In the Flex radio, it's measured in dBm, so you can actually get an actual measurement. And this is what we call a waterfall display, which is showing you over time what the signal is, up to 20 seconds. In the way we have it set up right now. So what you're kind of seeing here are the Morse code dots and dashes. Now I'm much wider than I need to be in bandwidth for this signal, so let me go down, let me change modes to CW. That'll probably make me, much smaller, and let me retune. So this is a CW signal. See, it does have some bandwidth, but nowhere near as wide. This is a 400 hertz bandwidth filter that we're using right now to receive the Morse code. So I just wanted you to actually see those signals so that you have in your mind, when you get your HF receiver, you'll be able to identify what you're seeing. All right, let's move on to another modulation mode with the HTs that we talked about, for example, and even there are mobile radios and home radios as well that use FM. FM is where you have modulation. Here's your audio modulation. This is a microphone that comes in, is amplified through an amplifier, and directly modulates, in this case, a varactor diode. And this varactor diode is in an oscillator stage. Here's the oscillator stage. And you're actually changing the resonant frequency of this circuit here by changing with the audio amplitude. So in this case, for FM, modulation is directly applied to an oscillator. When you directly apply modulation to an oscillator, also known as a reactance modulator in this case, that you will get FM. And the standard bandwidth for an FM signal is between 10 and 15 kilohertz for ham radio communications purposes. For broadcast, it's different, but we're not concerned about that. Now, this is FM, frequency modulation. I said phase modulation was a cousin. In a phase modulated transmitter, you have an oscillator over here that is independent. It's fed in over here. You have your modulation here with, again, a varactor diode that changes its reactance in accordance with the audio, and it will pull the phase of that oscillator signal up or down depending on the modulation characteristic. For a phase modulated transmitter, the modulation is applied to a point after the oscillator. And when you do that, you get phase modulation. And remember, in FM, the frequency is changed by the modulating amplitude, the microphone amplitude, for example, whereas in phase modulation, the phase is changed by the modulating amplitude and by its frequency. A higher audio frequency gives more carrier modulation. Now, a receiver on the other end, a receiver that can receive FM, will also be able to receive phase modulation. Both are called angle modulation. We're just doing kind of an overview of that right now. And so here's a chart with FM and PM waves. It's kind of hard to tell the difference. They look very much the same. All right, we mentioned oscillators. You might remember from the technician class that oscillators are an amplifier with positive feedback through a frequency determining filter. And it's this frequency determining feedback circuit or filter that determines at what frequency that this stage will oscillate and output, in this case, a sine wave. And one of the more common oscillators back in the day with novices for sure was a crystal oscillator. Novices, back in the 1960s when I got first license, we were required to use crystals to determine our transmit frequency because they're very extremely stable and didn't have a lot of noise or other issues. So excellent frequency stability, but you're limited to one frequency because of the oscillator, the crystal only oscillates at one frequency. So here's our amplifier, it's a field effect transistor. Here's the feedback from the amplifier going through this crystal and being fed back to the gate of the amplifier. And an equivalent circuit for a crystal is a resonant circuit, the equivalent of inductive and capacitive reactance. So this is a crystal filter, very stable on one frequency. We wanted always to upgrade from the novice class so that we could use a variable frequency oscillator. We didn't have to buy crystals anymore. And variable frequency oscillators in the day were made using inductors and variable capacitors, typically. So it was also known as an LC oscillator. So here's a series resonant circuit. Mostly they were parallel resonant circuits, and it's when the reactance of the capacitance and the reactance of the inductance are equal, you can use this formula to calculate, and that will give you the resonant frequency of this circuit. This circuit was also known as a tank circuit. I only put this picture in as a memory aid. It has nothing to do with the military. But the tank circuits were used as the frequency determining filter for oscillators. And the values of L and C in the tank circuit determined that frequency. And usually one of them was made variable so that you could change the frequency easily. So those were LC oscillators. You'll still see them sold at ham fests as external VFOs. They had their issues. They were tube type, so they had to warm up. Usually they were very drifty until they got to a stable operating temperature. Even then, they had a tendency to drift in frequency up or down. And so people were always looking for new ways to generate a reference signal or your transmit carrier signal that was stable but was also adjustable. And because of that, they came up with direct digital synthesis. And its claim to fame is that it has variable frequency with crystal oscillator stability. Well, yay, that's a win. It's not perfect. Inside a direct digital synthesizer are all of these steps and circuits. There's a phase accumulator, it's a phase lock loop. There's a lookup table which contains the amplitude value of a sine wave, for example. There's a digital to analog converter, a low pass filter. And one thing about DDS, it has no what they call phase noise. It's very stable in frequency, but it does sometimes output birdies or spurs. A lot of inexpensive shortwave radios that you might buy from China, for example, if you look at the reviews, sometimes they'll say there are birdies on this frequency and this. They're talking about false signals that just appear in the receiver because of direct digital synthesis. All right, let's move on to a completely different topic. In receivers, well, and transmitters, we want to change frequencies sometimes. We want to move from one frequency to another frequency. And in doing that through a stage called a mixer is a process known as heterodyning. It was invented by Reginald Fessenden, and it creates new frequencies by combining or mixing two original frequencies. Let's look here at a mixer. So here we have a signal on 7150 megahertz in the 40-meter band, and we have a conventional radio that has an intermediate frequency of 455 kilohertz. And that is a standard. That all the American 5-tube radios typically used 455 kilohertz. Many car radios used 455 kilohertz as an IF frequency. A lot of ham equipment, if it was single conversion, Radio Shack's DX150 or 160 used 455 kilohertz as an intermediate frequency where they could amplify the signal and filter the signal for bandwidth. Well, to get this frequency, 7150, to this frequency, we had to go through a mixer, and we would mix a local oscillator frequency of 7.605. And when we did that, you would get 4 signals on the output of the mixer. The original 2 frequencies, the sum of both, and the difference between both. In this case, if you get a calculator out and you take this frequency minus this frequency, you'll find out it's 455 kilohertz. And that's the one we want, and we would put filters at that point to only allow 455 kilohertz on through to the next stages of the radio. So, we start out with an RF frequency, let's say on 40 meters. It may be amplified, then it would go to a mixer, then it would go to an intermediate frequency amplifier, and then passed onward to audio stages. And you do this using a local oscillator signal that would be either above or below the desired frequency by 455 kilohertz in the case of that frequency IF. There's a problem with that. We're going to talk about that here in a second. I want to point out something. Ham radio, well, all radio is just a little bit over 100 years old now. And back in the day with tube type equipment, there were limitations on what could be done. They couldn't do direct digital synthesis back in the day. And back in the day, they had a desire. They needed to operate on VHF frequencies, but they didn't have the technology to directly create those frequencies. And so early VHF radios such as those being used by the police or whatnot, were tube-type radios that look something like this or something like this here, and they would be used in police cars or for construction equipment, things like that. They might be mounted in the back, the trunk area. They used elaborate vibrator power supplies that would actually create square waves through mechanically, and then use those to develop high voltage through transformers. Kind of elaborate. But to get up to the higher frequencies, they couldn't get the things to oscillate up there. So what they had to do is they had to do their generation with a low frequency carrier oscillator, amplify it, and then multiply it once, twice, maybe 3 times in order to get out on, let's say, a VHF frequency. We're going to talk more about this specifically coming up, but I want to introduce frequency multiplier stages. Again, what we do is we input a signal. Now, this is a transistorized version, but it works with tubes as well. And you tune the output tank circuit not to this frequency, but maybe to 2 megahertz, the second harmonic. And then you only get out 2 megahertz. Kind of nifty. These are called frequency doublers or even triplers. You can use them as well to go from a lower frequency up to a higher frequency. We'll talk more about that here because it has to also do with modulation for FM. Now, we mentioned filters, 455 kilohertz IF filters. I like the 12-step slogan, take what you like and leave the rest. Well, that's what a filter is all about. They pass a portion of the frequency range while blocking the rest of the frequencies. Radio frequency filters can be used for receive and for transmit. Here's some transmit bandpass filters that might be used, for example, in a solid-state linear amplifier, so that you put in a signal and you get only the band of frequencies out. And here's a schematic diagram of that sort of a thing. So we use design techniques. There are computer programs and other things that you can design filters. What we're concerned about is the filter's bandwidth. And by that we mean, what are the half power points? We also say, what are the 3 dB down points? So here's the center of the filter. Here's the amplitude, which we've set at 0 dB. And if we go down in frequency at some point here, it's going to be half the power. That is its lower frequency point, and here it goes down to 3 dB down. That's its upper frequency point, and then we measure here and we say that's the bandwidth of this filter, the half power point, or the 3 dB down point. So that's as far as the filter's bandwidth. Now, when you install a passive filter in a circuit, whether it be an IF amplifier or something like that, it's going to have some loss just from being there. So in this case, we're sending in a 10 dBm signal into this filter, and we're getting out an 8 dBm filter. So there was 2 dB of insertion loss. That's insertion loss with any passive filter. By that I mean it doesn't have any amplification built into it. That's normal. You amplify later to make up for that. We looked at a bandpass filter before. There's also low-pass filters. There's high-pass filters. And the cutoff frequency of a low-pass filter is the half power point on the high end. So again, we're using the same definitions as well. Do you feel rejected? I'm wanting to remember here something called ultimate rejection. It's a filter's ability to reject signals outside its passband. So here we're looking at this filter's, now here's its bandwidth, rated bandwidth, the 3 dB points. But noise down here, it will actually filter out all of these signals down to the noise level. That's 30 dB. That's this filter's ultimate rejection. It's the ability of the filter to reject signals outside of its total passband. Any Monty Python fans? Now for something completely different. Come back to me just for a second, Bruce. So I've been very blessed. worked for the Voice of America for about 20 years on international shortwave. But prior to that, I worked for television stations, PBS and a commercial NBC affiliate up in Michigan. And with analog TV, engineers who are responsible for the transmitter and cameras and things like that, we would have waveform monitors and vector scopes. And I just wanted to point to the slide here. This is a vector scope. This is for color signals. It's a color bar test signal that is up on the video output right now. And I want you to note that this axis here has the letter I, and this axis here has the letter Q. I and Q, in phase and quadrature. Something magical can happen with I and Q signals. And I and Q signals in the TV realm were analog signals, but I and Q signals can also be in the digital realm as well. So we just want to introduce you to the concept of I and Q signals. They're signals in the same frequency range, but they're shifted in phase by 90 degrees. And so if we had two sine waves, well, this is what they would look like. Here's a little closer view. So here is, they're same signal type, sine waves in this case, but they're very 90 degrees apart. Well, in the color signal for analog television, the I and Q signals were used to generate the full color spectrum that would be transmitted and reproduced. And interesting things can happen when you add I and Q signals together. Here's kind of a graphic which shows the two signals and the output from it. The whole point is, these are with sine wave signals, they're not complex, but you could actually inject complex signals, I and Q, and with the right I and Q signals, you can generate any RF signal. So any RF signal can be generated with the right I and Q signal. So you've got simple signals coming in, and you've got complex coming out. Also, I and Q, with any RF signal, it can be shifted in phase into I and Q signals, and any signal can be demodulated with in phase and quadrature. We're not going to go into the math. We're not going to go into, you just have to trust me on this. But they're used in radios, especially software-defined radios nowadays, where you have signals coming in, you have the ability to generate them into I and Q signals, and then it could be analog here in this case. But remember, I said can also be digital. So whereas we might have analog I and Q, as we're looking at up here on top, you could actually have digital to analog converters involved and convert them together, then DNA them, or you can actually convert them independently and combine them digitally. And that's what software-defined radios make great use of. An SDR is one in which most major signal processing tasks are handled in software. So this is my Flex 6600. This is the radio that's downstairs in the workshop, and we saw already earlier this evening. This is their Smart SDR software, which is another way that you can control the radio using a computer. Smart, funny things can happen with SDRs. All right, let's answer some more questions. So which of the following are basic components of a sine wave oscillator?
Filter?
Yes, a frequency determining filter and an amplifier operating in a feedback loop. And what determines the frequency of an LC oscillator?
Charlie?
Yeah, the inductance and capacitance in the tank circuit. I like to think of it as a tank of electrons sloshing around at one resonant frequency. And which of the following is characteristic of a direct digital synthesizer?
Delta.
Yes, it has variable frequency output with the stability of a crystal oscillator.
Longest answer.
And yeah, it is. What term defines a filter's attenuation inside its passband? So we're inside.
My nickname in high school, ultimate rejection.
No, that's not it.
Insertion loss.
Insertion loss. We won't
Insertion
go
loss.
there. But yeah, A, insertion loss is the filter's attenuation inside its operating frequency range. Yeah. And so what is the phase difference between the I and Q RF signals that software-defined radio equipment uses for modulation and demodulation?
Bravo.
90 degrees apart, indeed. And what is an advantage of using IQ modulation with software-defined radios?
Bravo.
We won't go into the math, but all types of modulation can be created with appropriate processing.
I knew that.
And which of these functions is performed by software in a software-defined radio?
Delta.
You got it. That's a trick question. Filtering, yes. Detection, yes. Modulation, yes. All of those choices. And what is the frequency above which a low-pass filter's output power is less than half the input power? What do we call that?
Charlie.
The cutoff frequency. That's the cutoff frequency. And what term specifies a filter's maximum ability to reject signals outside its passband? This is high school.
Yeah, ultimate.
Yeah, ultimate rejection. I feel for you. That was me too. All right. The bandwidth of a bandpass filter is measured between what two frequencies?
Bravo.
Not
Alpha.
alpha. It's the upper and lower half power
Oh,
points.
yeah.
Now, interestingly, cutoff is the half power point, but I don't know what roll off is. All right. So, what emission is produced by a reactance modulator? So, okay, let me back up. What emission is produced by a reactance modulator connected to a transmitter RF amplifier stage? Let me phrase it another way. It's not connected to an oscillator.
Bravo.
It is, Bravo. Phase modulation. When it's not connected to an oscillator and you have a reactance modulator, it's going to be phase modulation. And what is another term for the mixing of two RF signals? I think Mr. Fessenden. Yeah, heterodyning, which is why we call the old classic radios super heterodyne radios. More about that coming up. And what is the stage in a VHF FM transmitter that generates a harmonic of a lower frequency signal to reach a desired operating frequency?
Delta.
That's a frequency multiplier. And what combination of a mixer's local oscillator and RF input frequencies is found in the output? So we've got a mixer,
C.
yeah, with the sum and the difference plus the original two frequencies, but they don't have that here. But so sum and difference. All right, doing great. Section 5.3 transmitters, and then I think we get to take a break. You'd like to have one of these in your ham shack. This is a front panel from a Marconi B6128, which we had in VOA, 500,000 watts. You don't want to pay the power bill, however. So the very first voice mode we already mentioned was amplitude modulation. Again, it was our Canadian friend, Reginald Fessenden, in 1900. He generated an AM signal, and the first words that were sent were, "Hello, 1, 2, 3, 4. Is it snowing where you are, Mr. Thiessen?" and it went 1 mile. So that was the beginning. And amplitude modulation, we looked at this before. This is in the time domain. We're looking at the waveform created by connecting the peak values of the modulated signal components. The components are the modulating frequency and the RF carrier frequencies. And when added together, this is the envelope that you get in the time domain. So amplitude modulation has the carrier frequency, the lower sideband, and the upper sideband. Well, there are a lot of smart people that came along, and Edwin Armstrong is another one of the pioneers. And in 1933, he came up with a circuit that is known as a balanced modulator. And a balanced modulator does an interesting thing. It generates a double sideband suppressed carrier signal. By that we mean it has a lower sideband, it has an upper sideband, but it has no carrier. That's interesting. And a balanced modulator, you can see, has this sort of math going on, but it's a double sideband output. And so if you were looking at a frequency spectrum, you'd be missing the carrier, but you'd have the lower sideband and you'd have the upper sideband. Well, this is kind of important because I don't want to go into the pioneering work that came into single sideband. I'll show you a book here in a second. But single sideband was a theoretical thing back in the 40s and 50s. There are folks in the Midwest that were involved in coming up with a single sideband as a technology. I always say that the Strategic Air Command had a big part in it because they needed to communicate by voice with their long-distance bombers at great distance. And AM radios weren't cutting it. They wouldn't do it. But Collins Radio proposed to Strategic Air Command that they try single sideband, and it worked. And so there are two methods for generating single sideband. The phasing method, I think, was the first, actually. And then Edwin Armstrong came along with his double sideband signal from the balanced modulator. So we have the phasing method and the filter method of generating single sideband. We're going to talk more about that in a second. So in the Midwest, Central Electronics, a firm that was pioneered by a gentleman named Wes Shum, pioneered the use of phasing to generate single sideband. And we won't go into the methodology. There's a lot of math and whatnot, but you combine signals together such that you're able to eliminate the other sideband. And some of the old original equipment still exists today, and in fact, the late Bob Heil actually put together a radio system using the original Central Electronics phasing generator for single sideband. Well, let's let him tell us about it.
This is the Central Electronics, and this is how I tuned it up. You'll hear the receiver. We select the band, 80 meters, 75 meters. Then we're going to put this in the carrier null. Now watch. We're going to take those two out of phase, and away went the carrier. There's our carrier null. You can hear in the receiver when I had it up, but very carefully, I'm nulling those two signals, just like with those two microphones. And when we get it all correct, a little eye up on top will tell us, but then you can also listen in the receiver. Now we're going to set the max level, and you're going to hear that signal through a receiver when I bring up the microphone.
1, 2, 3, 4. Hello, 1, 2, 3, 4. 1, 2. This is K9EID. K9EID. Hello, 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 hello. 1, 2, 3, 4. 1, 2.
I tuned it off frequency.
1, 2,
so
3, 4.
You knew that you're listening to a sideband signal.
On a Central Electronics 20A. and receiving on a CM1 Mosley receiver.
There's the little receiver you're listening to. And I just had it in the background.
EID,
And
K9
there's
Echo
my scope.
Delta.
And everybody needs a scope.
Electronics
Everybody needs a
28,
scope.
600L.
But there's the baby. 600L, no tune linear. It's got a band switch and it's got a meter switch. And these guys today come along with their tens of thousands of dollars in amplifiers. Look at that. Isn't that beautiful? Look at that, George. Is that cool, George?
I love it.
I just thought it'd be kind of fun to let everybody see why George and I and Lynn and all these guys are so pumped up about this stuff. It is fabulous. Go to a ham fest, find a 20A, send it down to Nick. We're going to have Nick on in a few weeks. It'll probably be the first or second week of February. We'll keep you posted, and Nick and George will be back, and we'll talk a little bit. We're gonna.
So that was Bob Heil, just a real pioneer in amateur radio and in audio, in rock music. A fascinating guy. You can look into Bob Heil and his history. We lost him a little over a year ago, I think, and kind of missed the guy. But anyway, come back to me just for a second, Bruce, if you would. There is, speaking of memories and whatnot, there is a book out. I just want to make sure you see about it. It's Dominic Tusa, I think, was the author. It's Wes Shum, Amateur Radio's Unsung Hero. In our email that I send out tomorrow, I'll send you a link to this book. It talks about Central Electronics. It talks about his early career working in Chicago and the way things that got developed. But as you saw there with Bob, doing the tuning and whatnot, the phasing method of generating single sideband was too difficult for most hams. Vacuum tubes drifted and they required retuning. It produced a very clean output when it was properly adjusted, but it lost favor when they came up with the double sideband balance modulator and the filter method. Look how the filter method works. You have your audio coming in, you have your radio frequency carrier coming in into the balanced modulator, which remember outputs both upper sideband and lower sideband, and then you have filters, RF filters that only select one or the other to be passed on to the rest of the transmitter stage. Much, much simpler. And so the filter method took over and was the standard for generating single sideband. So I would say the phasing method is dead, right? No. Along comes software-defined radios. Remember the definition. An SDR is one in which the basic radio functions are performed in software. And the phasing techniques that you saw Bob Heil have to do manually there are easily done in mathematical functions in software-defined radios. So most SDRs use the phasing method to create single sideband. So it's back. All right, let's move on. This is a completely different topic, but the biggest operating oops that you can ever have, and it has to do with DX. If there's a DXpedition, for example, on the air, like right now, there are a bunch of DXpeditions from Guinea-Bissau and Bouvet, there's a gentleman in Fiji. They're operating right now, and if you want to work them on single sideband or in CW even, you need to know about, and remember I said I want you to be a good operator and I want you to know your radio and know your signals. You need to know about split operation. Split operation is where the DX is transmitting on one frequency, but the DX is listening on another frequency. And they will tell you, listening 5 up, or listening 5 to 15 up. That means 5 kilohertz up, or 15 kilohertz up. And that's where knowing your radio and how to set it up for split operation is important. You'll hear the Italians call it split, split. That's when operators don't know it's split operation and they transmit on the DX frequency. you need to know how to put your radio into split operation. So here's my example from Mr. Mauritius. Mr. Mauritius up there on top is transmitting on a frequency here in the 20 meter band. And you here in the United States are listening on that frequency. That's great. But he tells you, I'm listening 5 kilohertz up. And that isn't fixed. It can be 5 kilohertz and a little bit more, a little bit less. And you then are supposed to be transmitting up here. Don't transmit on the DX frequency, although it will happen. And that's what I say, it's the biggest, most common oops. So a radio with dual VFOs, variable frequency oscillators, can be used for split operation. You can set it up so that you receive on VFO A and you transmit on VFO B. And as long as you keep them straight and keep them, you're transmitting on the right frequency, everything works out just fine. You can also then monitor both frequencies, so you can hear the DX maybe in one ear, and you can hear your competition in the other ear, and that helps you sometimes to time out and know where the DX is listening. So let's go briefly back over to the Maestro and see if we can set it up for split operation. First, let me go back to, let's go to the 20 meter band. We're not going to transmit any signals. All right, and we are on upper sideband. So let's say, I'm going to go up a little higher. All right, let's say this is our DX signal right here. We have VFO A, or slice A as they call it, there. I'm going to activate slice B. All right, now we have slice B. Note that this is 14240. Flex is smart. It actually comes up automatically 5 kilohertz up. So then the other thing, if this is where the DX lives, this is where we want to transmit. This is the important part. You want to transmit over to the B slice. And in this way, you can be listening on the one frequency, the DX frequency, and transmit where the DX is listening. That's split operation. And each and every radio in their instruction manual will have a guide as to how to set it up for split operation. So your radio is probably a 100-watt output radio, and most are. But you may want to operate at higher power levels. And with the general class license in your frequency range, you can operate at up to 1,500 watts. In order to do that, you're going to have to use a linear amplifier. And the most cost-effective, the cheapest linear amplifiers are still tube type linear amplifiers. And such an amplifier requires tuning the output tank circuit and the load capacitor in order to operate properly. This was an amplifier that I built and owned for many, many years, the Heathkit SB1000. It's a single tube amplifier. It has a plate tuning capacitor here, a plate loading capacitor here, and a band switch, a band selector switch. All of these have to be set up manually and adjusted. The procedure for tuning an amplifier is to drive the amplifier with a low power RF, maybe 510 watts. You tune the plate capacitor for a dip in plate current. Then you adjust the loading capacitor for maximum output. Then you increase the drive from 10 watts maybe up to 30 watts. Retune the plate capacitor for a dip, and then adjust the loading capacitor for maximum output not to exceed the tube's ratings. Well, that's pretty involved, but it works, and it works very well. And so if you want an amplifier and for the lowest cost, a tube amplifier is something it's kind of like driving a stick shift, manual transmission. Not so many people can do it anymore, but it can be very effective. And so that's a skill that you might want to learn. Newer amplifiers are solid state amplifiers that don't require this sort of tuning. Amplifiers may also have something called automatic level control. It's a control signal sent from the amplifier back to a transceiver that reduces drive power in the presence of too much drive. And there's also a push-to-talk circuit that has to be connected between your radio and the amplifier. Some older tube-type amplifiers actually have PTT circuits that operate on 110 volts AC, which exceeds the rating of most solid-state transmitters today. So you have to know about these things. Here's an interconnection from a Kenwood TS570 to a Kenwood TL922 linear amplifier, for example, where it's got PTT and the ALC coming back to the radio here, and the RF drive from the radio coming on coax into the amplifier here. Amplifiers can be used for all sorts of different modulation, CW, radio teletype, data signals, single sideband voice example. Here's a trick question. How much output power is output on a single sideband transmitter when you have your microphone, you key up the microphone, but you don't talk? How much output power is there? Anybody?
0?
0 is correct, because without the carrier and without any modulation, you're not generating a sideband. You have to talk before you're going to get any output power. And so you have to keep that in mind when we're talking about ALC with the amplifiers, where it's sending a correction signal back to the amplifier. There's no RF output from a single sideband transmitter unless you are talking. And if there's too much ALC coming back from the transceiver, coming back to the transceiver from the amplifier, if you see that, one thing you can do to minimize that is turn down the mic gain, turn down the audio level, and when you do that, then things will balance out. That's what they're talking about with ALC level coming back from an amplifier to a transceiver. If there's too much, then turn down the mic gain, and everything should balance out. Also, with a tube-type amplifier, even some solid-state amplifiers that use relays for transmit-receive switching, there's always got to be a delay between when you're receiving and then start transmitting before RF can get through the amplifier. That delay prevents any arcing on the relay contacts, because if there's arcing, also known as hot switching, you'll get carbonization of the contacts on the relays, and all of a sudden you won't be able to hear anything anymore, and you'll get very low output power as well. So it's a transmit delay adjustment. It prevents RF energy from the transceiver until a time that you've set has elapsed. It might be 10 milliseconds or whatever that number is, to prevent hot switching. Now, more modern amplifiers use pin diode switching, and that is not mechanical in any way. It's electronic with a diode. It happens instantaneously. This becomes less and less of an issue. Also, delay adjustments, if you're going to be doing Morse code. There's some other TX transmit delay adjustments called hang time and other things that you just need to be aware of. If you get a tube-type amplifier, depending on the design, the SB1000 didn't need this, but especially if you've got two tubes and they're in push-pull, you may need to neutralize your amplifier, especially if you change tubes. What you're doing there is you're adding equal but out-of-phase signals to each of the tubes to cancel out unwanted feedback. Inter-element capacitance in the tubes can cause the tubes to oscillate if you don't properly neutralize them by sending 180-degree signals back. Here's a neutralizing capacitor being sent over to this guy and a neutralizing signal being sent over to this guy. Your manual for the amplifier will tell you if you need to do neutralization and how to do it. I just want you to be aware of that fact. Solid-state amplifiers, like the ones that I have, Elecraft KPA 500 or my RF kit, they use solid-state devices. In one case, LDMOS devices. For those, you have to change the band that you're operating on. That can be done automatically sometimes with computer-aided transceiver control. too much drive power is the single most frequent cause of damaging a solid state amplifier. Typically, they don't require a lot of power to generate legal limit output. So know your amplifier, know how much is too much, and try to make sure that you minimize so you don't overdrive a solid state amplifier. When you overdrive a linear amplifier, well, it causes clipping. We'll see that here in just a second. So how do we test amplifier's linearity, its ability to amplify low-level signals and high-level signals? We use something called the two-tone test. We're going to take a break here in just a minute. Two-tone tests are two non-harmonically related audio sine waves that are fed into a transceiver's microphone input, and then you monitor the output on an oscilloscope. And you're looking for jagged or non-linearity areas if you go from one power level to another. The two-tone test. You're using a monitor scope. These are ones by Kenwood, for example. I have one of these downstairs. And it even has a two-tone generator built in on this BNC connector where you can generate the tones, or you can use software, or there are hardware boards as well to generate the two tones you need for linearity testing of amplifiers. And again, I said if you overdrive, you're going to clip the output of the signal in your amplifier, and it's going to generate lots of harmonics and spurious output. You don't want to do that. So you want to make sure that your drive levels are moderate. Audio speech processing. Too much of a good thing is no good either. Now, audio speech processing is done in your transceiver, and it's done for a purpose. It raises the average power level of your signal, which increases the receive intelligibility at the receiving location. So you can have compression and audio frequency equalization or some of the adjustments that you may have, but too much of a good thing, it also can cause distortion. It can cause frequency splatter, or where you have a clean signal on the left there and a splattering signal there on the right, which is too wide. Also, too much of a good thing can, if you have the gain turned way up, you can pick up lots of background noise. Your dog barking in the background, etc., etc. Now, amplifier efficiency, how much output for RF, how much DC power is being used for how much RF output power you're getting. We're going to talk about that in dealing with amplifier classes. But you know what? I think we're going to take our break right now because we're at the 46 minute and I want you to get up and move around and stretch. Come back to me just for a second, Bruce. So let's go ahead. We'll take our 5-minute break now and then come back and then we'll look at amplifier classes, including a new class that is actually being popularized this year. So come back in 5 minutes. We'll see you in a bit. hope you got a chance to get up and move around and shake things off a little bit. I apologize. I think I was rushing a little bit toward the end there, and I caught myself and I said, let's just take a break and come on back. And so there's going to be an intermission slide coming up here, but we're going to go right over it here. But amplifier classes, that's where we left off. And we're talking about the amplifier and whether it be tube type or transistorized, and how much of an input waveform does the amplifier amplify. And it has to do with how the amplifier is biased or set up. If it amplifies the whole waveform, that means it's going to be on all the time, and that means it's going to be less power efficient. So that's also the definition of a linear amplifier, where if you've got a signal coming in, positive and negative peaks, you're going to get all of the positive and negative peaks amplified out on the other side. So Class A amplifiers, now we're talking about here a transistor, but this could be used in the output section, for example, of an RF power amplifier. A Class A amplifier is biased or set up such that for an input signal, whoops, let me turn on my laser pointer, which went off. There we go. So for an input signal, the transistor will create an output signal at a higher level that fully corresponds to the positive and negative peaks of the input cycle. So this is a Class A amplifier. This is a linear amplifier. It's amplifying everything. Its power efficiency is going to be the least efficient of all of the classes we're going to talk about, because the DC power is required by the transistor 100% of the time. Now a Class B amplifier, in this case we're using 2 transistors, and each of the transistors is biased Class B, and each of the transistors amplifies only half of the waveform. In this case on the top it's amplifying just the positive going, and on the bottom it's amplifying just the negative going. So if we're looking at one transistor, we've got the input signal here, but it's only outputting 1/2 of the input signal. So this is more efficient than a Class A because the DC power is required by that transistor only 50% of the time. Now there are some problems when it goes to 0 and it switches over to the other transistor to pick up the slack. That crossover point is a place where you can get distortion. It's called crossover distortion. And so instead of using Class B amplifiers, if they're going to do this sort of thing with 2 output devices, they'll typically bias them Class AB, which is somewhere in between Class A and Class B, so that you're actually amplifying, in this case, the positive waveform and a little bit of the negative. That gets rid of that distortion that I was talking about at the 0 point. It's more power efficient, Class AB is, than Class A, but it's less power efficient than Class B. And then Class C amplifiers, they amplify only just a very small portion of the input signal, just the tip, for example. But in this kind of an amplifier, if you follow it with a resonant circuit, you'll get this resonant circuit to fill in the gaps, to fill in the rest of the signal. And that's why Class C amplifiers can be used for signals that you don't worry about the amplitude variations. So Morse code, which is on or off, can use a Class C amplifier. FM signals, which are always at full power, and you're just varying the frequency, can use Class C amplifiers. So Class C amplifiers are more power efficient than any of the others that we've talked about before, because power is required by the amplifying device, in this case a transistor, 20% of the time or less. And the newest practical thing that we've got in amateur radio now is our Class D amplifiers, which utilize switching circuits to switch, in this case, MOSFETs, either on or off. And there's a lot of things that go into the development of the signals that go into these MOSFETs. And new radios from Flex Radio, the same people that build the Maestro and the 6600, their new Aurora line of transmitters, radios, and the radios from QMX Labs are using a new technique they call polar modulation. And both of these are Class D, very high efficiency on the output. In fact, the Aurora is said to be 90% power efficient. So this Aurora radio in and of itself is a 500 watt output radio that can be plugged into a 110 volt outlet. And if you go to the Hamfest, just we're down in Hamcation in Orlando, they'll put a CW key to the radio, put a brick on the key, and let the radio run at 500 watts for the entire run of the show. And they have a dummy load there, and you can measure the dummy load's heating up. But the radio is not. You can put your hand on the top of the radio and it's cool because of the power efficiency of Class D modulation, or as they're calling it, polar modulation. So amplifier classes and efficiency. Here's A, here's AB, here's B, here's C. These are in the analog domain. And then Class D and up, these are in the digital domain, where efficiencies, like for the Aurora, they say is 90% power efficient in the output stage. Wow. That's transformative in the radio community. All right, let's shift some gears. I love FM. Well, I don't, but it's okay. But in order to calculate bandwidth of an FM signal, remember we said for communications purposes, the bandwidth is between 10 and 15 kilohertz. We use something called Carson's bandwidth rule. And the actual formula is you take the amount of deviation and you take the highest modulating frequency. And you add them together and then you multiply it by 2. So in this case, the bandwidth would be 16 kilohertz. If you just keep that in mind and know about Carson's bandwidth rule, you'll be able to answer a question. Now, I mentioned those early radios, those early VHF radios that used frequency multipliers. They would generate their FM signals at a lower frequency and then use frequency multiplier stages to come up to the operating frequency on VHF. Well, an interesting fact is that the amount of deviation is also multiplied by the same factor. And this leads to a question on the test. So here we have an older radio with an operating frequency of 146.52 megahertz. The desired deviation is 5 kilohertz. All right. We start out with a low frequency oscillator of 12.21 megahertz. And if we do the math, we find that it must be multiplied 12 times in order to get up to 146.52 megahertz. So what do we have to have for the original low frequency oscillator deviation? Well, if we say it's going to be multiplied as well, then we can take 5 kilohertz and divide it by 12, and we get 416.67 hertz. That's the amount of deviation on that really low frequency 12 megahertz oscillator. That's the amount of deviation we need, that once it's multiplied up, then it'll become 5 kilohertz deviation, which is the standard for communications. So just want you to consider this concept. All right, here's some questions. What control is typically adjusted for proper ALC setting on a single sideband transceiver?
Bravo?
Yeah, it's not intuitive, but yes, transmit audio level or microphone gain is what you adjust to balance out the ALC coming back from a linear amplifier.
I think I knew that.
And what is the effect on plate current of the correct setting of a vacuum tube RF power amplifier's tune control? What are we looking for?
Alpha?
No, not alpha.
Bravo.
Bravo, we're looking for a dip in current. We're looking for a minimum. And you'll actually see it when you get your hands on your first tube type linear amplifier. As you adjust that control, you'll see it. There's a distinct dip at the operating frequency. That's where you want to adjust it. And why is automatic level control used with an RF power amplifier?
D. Harmony.
Yes, to prevent excessive drive. There we go. And what is the correct adjustment for the load or coupling control of a vacuum tube RF power amplifier? That's the other variable capacitor.
Bravo.
Not Bravo.
Delta.
It is delta. You actually, for the desired power output or the maximum power output without exceeding maximum allowable plate current. And each tube will have a rating for the maximum allowable plate current. It'll be in the book, the instruction manual. So what is the purpose of delaying RF output after activating a transmitter's keying line to an external amplifier?
Charlie.
It's the longest answer. To allow time for the amplifier to switch the antenna between the transceiver and the amplifier output, preventing hot switching. And what signals are used to conduct a two-tone test? Not the longest answer.
Bravo.
Two non-harmonically related audio signals. And by harmonically related, I mean you can't have 1,000 hertz and 2,000 hertz. They're an octave apart. That wouldn't work. But 1,000 and 1,500, that would work. All right, what transmitter performance parameter does a two-tone test analyze?
Alpha.
They're called linear amplifiers, and we're testing the amplifier's linearity using the two-tone test. And what is the purpose of a speech processor in a transceiver?
Charlie. Alpha.
It is alpha. It's to increase the apparent loudness of transmitted voice signals at the receive end by raising the average power output of the transceiver. So you're using compression and maybe equalization. Oh, how does a speech processor affect a single sideband phone signal?
Bravo.
Yeah, it increases the average power. That's just what I said. Okay, what is the effect of an incorrectly adjusted speech processor? Read carefully.
Delta.
Yes, you could have distorted speech, you could have excessive background noise, you could have excess intermodulation products, all of those. And what frequency range is occupied by a 3 kilohertz lower sideband signal when the displayed carrier frequency is set to 7.178 megahertz?
Charlie.
Exactly, 7.175 to 7.178. And what frequency range is occupied by a 3 kilohertz upper sideband signal with the displayed carrier frequency set to 14.347? 14.347 to 14.350. Very good. And how close to the lower edge of a band's phone segment should your displayed carrier frequency be when using a 3 kilohertz wide lower sideband?
Alpha.
At least 3 kilohertz above the edge of the segment. Yes. You got to make room there for your sideband signal, the output. All right. How close to the upper edge of a band's phone segment should your displayed carrier frequency be when using 3 kilohertz wide upper sideband?
Bravo.
Bravo.
Yeah, at least 3 kilohertz below the edge of the band because you're using upper sideband. And what is the purpose of it neutralizing an amplifier?
Bravo.
Tubes can oscillate on their own at higher frequencies. So yeah, neutralization eliminates that. And which of these classes of amplifiers has the highest efficiency?
Delta.
Delta, which is class C in this case. Yes, indeed. And in a class A amplifier, what percentage of the time does the amplifying device conduct?
Alpha.
100% for a class A. And how is the efficiency of an RF power amplifier determined?
Bravo.
Yeah, Bravo.
Divide the RF output power by the DC input power. And which of the following describes a linear amplifier?
Bravo.
Yes, it's an amplifier in which the output preserves all of the original input waveform. For which of the following modes is a Class C power stage appropriate for amplifying a modulated signal?
Delta.
No.
Bravo.
But it's the longest answer.
So remember, Class C power amplifiers only amplify just the tip of the input signal, which is no good for anything that involves amplitude changes. Because for amplitude changes, you need the whole thing. So the only one that would work properly in this case is FM. Class C power bricks, for example, for VHF and UHF, may have a switch that says single sideband or FM. That's what this is all about. You're switching the power brick from a Class A to a Class C for greater power efficiency for FM. So what circuit is used to select one of the sidebands from a balanced modulator?
Bravo.
That's why it's called the filter method. You have an upper sideband filter or a lower sideband filter. And what output is produced by a balanced modulator?
Bravo.
Bravo.
Not Bravo. A balanced modulator produces double sideband suppressed carrier, double sideband modulated RF. And which of the following is an effect of overmodulation?
Delta.
We say you'll be creating splatter, it's excessive bandwidth. And what is meant by the term flat topping when referring to an amplitude modulated phone signal? I think I heard it.
Charlie.
Yes, Charlie. Signal distortion caused by excessive drive or speech levels, you clip off the top and bottom peaks. And what is the modulation envelope of an AM signal?
Delta.
Nope.
Bravo.
Alpha.
And the modulation envelope is something you would see on an oscilloscope display. It's a waveform created by connecting the peak values of the modulated signals, modulating and the carrier. All right. And what is the total bandwidth of an FM phone transmission having 5 kilohertz deviation and 3 kilohertz modulating frequency?
Or
Not Charlie.
oh, it's Delta.
Carson's bandwidth rule, 5 plus 3 times 2, 16 kilohertz. Here's Johnny. And what is the frequency deviation for a 12.21 megahertz reactance modulated oscillator in a 5 kilohertz deviation 146.52 megahertz FM phone transmitter? Do you remember?
Bravo.
Yeah, you have to take 5 kilohertz and divide it by 12 and you get 416 hertz. All right, so this is where we were going to have intermission, but now we're moving on to receivers. So the simplest kind of receiver is a super heterodyne radio. And I mean, crystal radios are even simpler, but this is what we're going to talk about here, where we have a signal coming in on, this is an 80 meter frequency. We have a local oscillator coming in here to a mixer stage. In this case, the mixing difference is actually an audio signal. 1 kilohertz is all the difference is between them. And so we're actually going right down to audio and right to headphones in this case. This is a radio that could be built and actually used, a very simple super heterodyne type radio. More conventionally, you're going to find something like this. Where you have your antenna, you have an RF filter to limit any out-of-band spurious signals, an RF amplifier to bring that signal level up a little bit, to a mixer where we have a local oscillator and the original frequency, and then we take either the sum or the difference of those, which probably is going to be 455 kilohertz. Then we'll amplify it in our intermediate frequency amplifiers and filters. Then we'll demodulate it and back down to audio. So this is what we call a single conversion radio. We have only one frequency conversion going on, from the input frequency to the IF frequency. And this is all well and good, except, remember I said that you could have the sum or the difference and have that be 455 kilohertz or whatever the IF frequency is. That means there are actually two solutions that will work. So let's say we want to receive this station. This is our desired station. And so we have our local oscillator be 455 kilohertz above that. And so the difference of this from this will be 455, and that works great. Except there's a second solution that also works if there's an incoming signal on this frequency. It's 455 kilohertz higher than this, and the difference between this and this is also 455. This is called an image. It's an unwanted signal that could be received by a single conversion radio. Some amateur radio receivers or shortwave receivers were single conversion radios. The Radio Shack DX150 that I mentioned earlier, that's a single conversion radio and had problems with images or false signals. So most manufacturers now for super heterodyne radios use at least double conversion, if not triple conversion. And that is where you have a first mixer that actually takes it up to a very high IF frequency, 50 megahertz maybe, and then you have a second mixer that takes it back down to a conventional IF frequency and then filtered and on out. So this is a double conversion superhet, and that's the difference between single conversion and double conversion, and we're doing double conversion because we want to eliminate the possibility of receiving an image frequency, the one that also has a solution. I told you earlier I love FM. Well, I want you to know that FM is discriminating. At least they'd like you to believe that. The demodulator in an FM receiver is called a discriminator. And that is used to get the audio out of a varying frequency FM signal. So keep that in mind. In both AM single sideband and FM radios, you may have an attenuator on the input. That's the ATT function here on the ICOM 7300. That attenuator actually will reduce the signal coming into a receiver, and it improves a receiver's ability to handle very strong signals. So that's a technique you can use sometimes to eliminate some interference. With super heterodyne radios that have an IF, the filters that you install in the radio, whether they're crystal, ceramic, or otherwise, will set the bandwidth of reception. So you have a filter for CW and you have a filter for single sideband. Why do we use these filters, and why do we use the various bandwidths of these filters? Well, we saw on the Maestro there on the display that for CW, for example, we made a very narrow filter. We do that to match the receiver bandwidth to the transmitted bandwidth in order to get the maximum signal to noise. So that's why we have different bandwidth filters, is to eliminate noise or signals that we don't want to receive. Sometimes signals will appear, especially if you're on single sideband. There may be a carrier that'll come up, or we sometimes call it a heterodyne. And it's a signal, it's an unwanted carrier that's within your receive passband. Well, many radios have what are known as notch filters. With the push of a button and the twist of a knob, you can actually eliminate that errant signal that's trying to come into your receive passband. And the notch filter then allows you to hear the desired signal very clearly. Some of the notch filters are automatic, but most are manual, where you activate them and adjust a knob to get them to eliminate the unwanted carrier. If you're going to be listening to Morse code signals and you have an interference problem from a nearby signal, there may be a button on your radio that is called CW reverse. And what it does, it flips where the beat frequency oscillator is. Either the beat frequency oscillator can be above the desired signal, or it could be set to reverse to be below the desired signal. And when it's in one position, you see you've got your desired signal and you've got an interfering signal in your bandpass, where if you flip it, the interference signal is outside of the bandpass and you only hear one signal. So it's a way to shift a receiver's passband, and it may allow you to eliminate interference on CW signals. That's the CWR, or CW reverse button. Many radios have something called IF shift, also known as passband tuning, where you can actually adjust the filter skirts up and down. It also is here to eliminate interference. That's why these controls exist, trying to get you to be able to hear the desired signal better. If you're going to be operating mobile, or even at home sometimes with electric fences, a noise blanker can be your friend. A noise blanker is switched squelch that senses high pulses, repetitive pulses in your signal, and can remove that by squelching it out. And all of a sudden, then all you hear is the desired signal, with some brief pauses that you don't even notice. And so noise blanker can do that. There are some radios that have something called a clipper circuit. That's for excess amplitude signals. That's not to be confused with the noise blanker. There's not a question on this anymore, but just to make that aware. Nowadays, digital signal processing is what's going on in most modern radios. And digital signal processing can be external. This is an old Radio Shack DSP unit that operated at the audio level. And it had a noise reduction function there that could actually reduce background hiss and static and noise. It worked okay. But nowadays, ever since the mid 90s, the DSP functions are built into radios as early as the IC756 from ICOM. Digital signal processing does it all. It does the notch filtering, it does the IF filtering, it has a noise blanker functions, audio peaking filters, and it's all done in the digital domain. Another nice thing about the DSP is that with DSP you don't have to buy filters. Remember I said you had to buy a filter for CW and had to buy a filter for a single sideband. You don't with DSP. It's all done in software, all the filtering. Again though, with too much processing, it gives distortion. So always be aware of that if you start turning all of these things on all of the time, it's not going to work well. So like for noise blanking, you don't want that on all the time. All right, let's move along here, still with the receivers. Receivers, whether they be the Flex or an older Kenwood or whatever, is going to have an S meter. S meters, you may have seen, go up to S9, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then above S9, it's in decibels, plus 10 dB, plus 20 dB, plus 30 dB, and so forth. Each S unit on the S meter, the standard is 6 dB per S unit. 6 dB is 4 times power gain, which means that if we're sending a signal out and it's being received at a distance as an S5 signal, and I'm transmitting 100 watts, in order to get that signal up to S6, I have to go to 400 watts output power, not 200, 400 watts. So each S unit represents a 4 times or 6 dB power increase, and an antenna with a directional gain of 6 dB also gives you that 4 times power increase. So that's where we say antenna gain can be most important, because it's on transmit and on receive as well. And if you've forgotten decibels and their quantities, here's a little chart that I've included that you can take a look at. I mentioned the DX150 a little earlier tonight. Well, here's that radio. It was one of my novice receivers. And inside this radio, they have a circuit with the IF signal coming in, and it's a product detector stage with 2 diodes and an RF signal coming in from a beat frequency oscillator. This is the circuit that allows you to receive single sideband by injecting a signal that replaces the carrier that was eliminated when we generated single sideband. And when you get the BFO adjusted right and the tuning adjusted right, then you can demodulate single sideband signals. But single sideband signals are demodulated in an analog radio in a product detector. All right, questions? What is the purpose of the notch filter found on many HF transceivers?
Charlie.
Bravo.
It is Bravo. It's to reduce interference from carriers in the receiver passband. And what is the benefit of using the opposite or reverse sideband when receiving CW? Not Bravo.
Alpha.
It's all about eliminating interference, so it's Charlie. It may be possible to reduce or eliminate interference from other signals. And how does a noise blanker work?
Bravo.
Not Bravo. I called it squelching, but it's by reducing receiver gain during a noise pulse. It senses when the noise pulse is and reduces gain briefly during that noise pulse. So what happens as a receiver's noise reduction control is increased? Remember, too much of a good thing.
Alpha.
Yeah, received signals may become distorted, so use it with moderation. And what is the purpose of using a receive attenuator?
Alpha.
Yes, it's to prevent receiver overload from strong incoming signals. And what does an S meter measure? You see that? Yep, Charlie, received signal strength. S meters on receivers. And how does a signal that reads 20 dB over S9 compare to one that reads S9 on a receiver, assuming a properly calibrated S meter?
Delta.
So 20 dB is the same as 10 times 10 or 100 times more powerful. And how much change in signal strength is typically represented by 1 S unit? Yeah, 6 dB or 4 times. And how much must the power output of a transmitter be raised to change the S meter reading on a distant receiver from S8 to S9?
Charlie. 4 times.
4 times, exactly. And how is a product detector used?
Delta.
Yes, it's used in a single sideband receiver, like that realistic DX150, to extract the modulated signal from a single sideband signal. All right. And which of the following is an advantage of a digital signal processing filter compared to an analog filter?
Alpha.
Bravo.
It's alpha. A wide range of filter bandwidths and shapes can be created just in the DSP.
It's also Bravo kind
No, actually, with a DSP, you require more digital components.
Or you don't have to buy filters.
Well, but yeah, filters are not considered digital components, they're considered analog components.
Okay.
Yeah.
So it's not the longest answer in the day.
Yeah, no, don't count on that. So which parameter affects receiver sensitivity? Read carefully.
Alpha, again.
Alpha is true,
Because Delta,
bandwidth is true, and input amplifier noise figure, all of those choices affect receiver sensitivity. We didn't have the time to go into them in depth, but yeah. All right, which mixer input is varied or tuned to convert signals of different frequencies to an intermediate frequency?
B, Bravo.
That's the local oscillator. That's one of the inputs to the mixer. And what is the term for interference from a signal at twice the IF frequency from the desired signal?
Bravo.
That's the image. That's the image signal, image response. And why is it good to match receiver bandwidth to the bandwidth of the operating mode?
Delta.
Delta.
Yeah, it results in the best signal to noise ratio. All right, section 5.5, HF station installation. Here's my friend Bob's station up in Edneyville, at least it was. There's my old station at my old QTH over in Greenville. When I first came over here to Anderson County, then this was, oh, that's still in Greenville. And then here is in Anderson County using the Maestro. I had that set up there. And my VHF, UHF station with a Yaesu FT991A. Then I got upgraded to the ICOM IC7760. How is your station set up? Well, it's all up to you, how you put your station together. One thing though, no matter how you put your station together, you're going to want to eliminate radio frequency interference. You don't want signals to interfere with your reception. So you use grounding and bonding, shielded cable, ferrites are your friend on problem cables. You want to keep antennas far away from the ham shack in your house if you can, because that's where all the noise lives. And use balanced antennas that don't work against station ground. When you have two signals together, you have something called intermodulation. I'm going to jump over my story time because we're running out of time here. But back in Liberia, I had two primary radios. I was part of a missionary radio network there, and I ended up generating my own intermodulation interference in one of my radios. It was all down to signal diodes, these things right here, that were being overloaded by local signals. And the only way to eliminate that was, well, you had to disconnect the antenna lead from the radio. So I QRM'd myself with intermodulation distortion. Intermodulation distortion is interference caused by the mixing of two or more other signals in a nonlinear device, such as a diode. And we talk about intermodulation products. Just know that third order or odd products are the pesky ones, and they're close to the fundamental frequencies. These are the frequencies we're concerned about initially, and these little guys right here are called the odd order or third order products. They might cause interference to our signals. All the rest don't. There's ways to calculate that. We don't have the time because we're out of time, but there are ways to calculate these frequencies. But third order or odd products cause the problems, all right? And RF in the shack, if you're transmitting and you get a radio frequency energy coming back in the shack, it can cause distortion. It can cause your transmitter to lock up and stay in transmit. Yeah, and it causes disconnects to USB and Ethernet and other control circuits. And how do you fight that? Well, you use grounding and bonding techniques, ferrites on problem cables, and bypass capacitors in audio circuits. Another problem with RF is it can cause RF burns on the chassis of equipment, and so you want to bond all radio chassis together. I'll send you a link to this video. You can watch it. It's about 90 minutes long. Standing up for standing wave. It's great. One of the things you take away from it, however, is that a ground wire is not necessarily a good connection. It depends on how long it is. And if it's a quarter wavelength long at the frequency you're trying to ground out, well, it becomes not a ground, and it becomes an open. And so you need to be concerned about that. And ground rods, though, can be your friend. It's not resonant on any frequency, but a ground wire can be a high impedance if it's a quarter of a wavelength long. Single point grounding is better than bus bar grounding. This is bus bar grounding up here. Single point is better. It reduces ground loops. And ground loops are a problem that can also cause problems in your audio. It can give you a hum in your audio. In RF, ground loops, you get distortion and lockups. And if you're going to go mobile and you're going to ground things out, well, you may need to ground and bond parts of your vehicle. And radio power connections should always go directly to the battery. No longer can you just connect to the negative lead to the chassis of the car. That doesn't always work anymore. And you can have noise and interference in your car from fuel pumps, onboard computers, the engine's electrical system, including battery charging. And if you're going to be powering your radio, if you're going to use that cigarette lighter, that might not be rated for the amount of current that you want to draw. It's better to take the power connections directly back to the battery. And if you've got RF in your microphone connections, little small bypass capacitors can actually eliminate some of the RF that might get into your microphone. And then if you've got arcing going on anywhere, that's a wideband noise generator, and you'll get it in your receiver. So can a telephone receive single sideband? Only very poorly. You'll get distorted speech. Can a stereo receive Morse code? Only very poorly. You'll get humming and clicking. There are 3 conductors in an RF coaxial cable, and it's the outer part of the shield that we're concerned about that can bring common mode noise and signals back into the ham shack. And so here's a ferrite toroid with a coaxial cable wound through it, which impedes RF current flow on the outside of a coaxial cable. Is your mobile antenna wife approved? Probably not. And for HF Mobile, it's the antenna that always presents the problem, because antenna efficiency is always pretty low. All right, last questions. We ran through this really quick. Which of the following might be useful in reducing RF interference to audio frequency circuits? I'm just going to tell you. Bypass capacitors. And which of the following could be a cause of interference covering a wide range of frequencies? You saw that arc. Well, arcing at a poor electrical connection will generate interference. We're at 34 minutes after the hour. What sound is heard from an audio device experiencing RF interference from a single sideband phone transmitter? Think of a telephone. You'll get distorted speech. What sound is heard from an audio device experiencing RF interference from Morse code transmitter? On and off humming and clicking. What is the possible cause of high voltages that produce RF burns? It's the ground wire. Yeah, very good. It has a high impedance on that frequency. You're keeping up. That's good. And what is a possible effect of a resonant ground connection? High RF voltages on the enclosures of station equipment. That's when the wire is a quarter of a wavelength long. Which of the following would reduce RF interference caused by common mode current on an audio cable? Ferrites. Yeah, ferrites are your friend. Ferrite choke on the cable. Or how can the effects of ground loops be minimized? Bond equipment enclosures together using star or single point grounding. What could be a symptom caused by a ground loop in your station's audio? Hum, hum, yeah, you got it, hum, alpha. Receive reports of hum. What technique helps to minimize RF hotspots on an amateur station? Bonding all equipment enclosures together. making sure they're all at the same RF potential. And why must all metal enclosures of station equipment be grounded? It ensures that hazardous voltages cannot appear on the chassis. I apologize for the rushing this last part. Which of the following direct fused power connections would be the best for a 100-watt HF mobile installation? If you're gonna, yeah, right back to the battery using heavy gauge wire to prevent voltage drop. And why should DC power for a 100-watt radio not be supplied by the vehicle's cigarette lighter? Because the socket's wiring may be inadequate for the current drawn by the transceiver, and you might let the smoke out of the car. All right, and which of the following most limits an HF mobile installation? The problem is always the efficiency of the short antennas on HF. And which of the following may cause receive interference in an HF transceiver installed in a vehicle? Could be the battery charging system, could be the fuel delivery system, could be the control computer, so all of those are possible. And how does a ferrite bead or core reduce common mode RF current on the shield of a coax cable? It's by creating an impedance in the RF current's path. And which intermodulation products are closest to the original signal frequencies? And for intermodulation, the odd order or third order products are closest. And what process combines two signals in a nonlinear circuit to produce unwanted spurious outputs? That's intermodulation. And which of the following is an odd order intermodulation product of frequencies F1 and F2? It has to do with this number 2 and the number in front of the F2, which is a 1. 1 and 2 is 3. That's a third order product. So 2 times one frequency minus the original frequency F2 gives you an intermodulation product that is close by. And that, ladies and gentlemen, is the end of chapter 5. Oh, I'm so sorry.
Thank you.
But
Thank you. Don't be sorry.
Dave, what are we doing next week?
Well, next week we're doing Chapter 6, which is Basics of Digital Modes. And digital is the hottest thing in ham radio right now in terms of new things that are going on. There's 5 sections. We're going to go through the entire chapter, and you'll be excited about some of this. There's some really good stuff in this chapter.
So I thank you for hanging in there. We're going to be close to 10 minutes over tonight. I have to look. Last year, was I over? I took it too casually, I guess. Anyway, thank you for hanging in there.
Yeah, no problem.
And
One question. I
Yes,
got
go
a
ahead.
tech question.
yeah,
Is it, I've seen vehicles when you're doing mobile and stuff like that, I understand getting everything bonded together to one ground. I've seen them hang chains off their vehicles so that it touches the earth actually, as they're like when they're driving or when they're stationary. Is it a good practice? Is it a practice? Does it make any difference?
I think the whole point of that was to remove static, maybe even when you were stationary, to give a path to ground, to remove static. I would think, though, if you're in motion, that's going to, it's going to be bouncing along on the earth. I would think that would generate noise as it makes and breaks that connection down there. I don't know of anybody in my local community that's doing it, so I would say, no, don't worry about it.
Yeah, I've seen shopping carts with chains on them for the same reason, for static electricity discharge.
Yeah. All right.
Okay.
See y'all next week. Thanks for hanging in there. 73, y'all.
Yeah, good night.
Thanks, guys.
Thank you.
Good night.